All right, last time we left off, we were talking a little bit about the actual nephron, and so now we're going to talk about really how this thing functions. So the filtrate, as we said, that's the part that comes out of the glomerulus and into Bowman's capsule, and this is what's going to contain some salts, sugars, amino acids, vitamins, as well as nitrogenous waste, but we're going to exclude the larger molecules, large macromolecules, such as proteins, fats, large carbohydrates, things like that. And once it gets through Bowman's capsule, there's three regions that we said. You've got the proximal convoluted tubules, the loop of Henle, and the distal convoluted tubules. And in the proximal tubule, this is the first part, and this is where you're going to selectively reabsorb those things we were talking about earlier, the ions, exchange there, the salt, sugar, things like that. And then the loop of Henle now, and the length of the loop of Henle really is going to be responsible for helping us concentrate the urine and really conserve the water. And you've got this sharp kind of hairpin turn down here. This would be the actual loop of Henle right through here. Okay, and the longer it is, the more concentrated the urine that you can actually be producing. And really, the drier environment, the longer the loop of Henle, the drier environment, the more loops of Henle really you have, and the longer ones you have. And then fish, living in the aquatic environment that they do, they don't have any loop of Henle because water is not an issue for them. Okay, so now this distal convoluted tubule, this is what's going to kind of empty into the collecting duct, and this is where the urine is actually going to get formed. So we can look through here. If we're looking just at the osmolarity here, the set point now that we've kind of talked about, just think about negative feedback, for instance, here. And if we're talking about something that looks like this, we could be discussing like the temperature in our living room with the furnace and so forth. Doesn't really matter. But the set point, trying to find my bearings here, milliosmoles per liter, 300 milliosmoles per liter is what we want to kind of keep it at. And if we get really thirsty and it goes up, okay, some mechanisms are going to kick into place that we'll talk about to kind of bring it back down to the set point. And then when it gets too low, okay, we've got like a lot of water in our diet, some things will kick into place we'll talk about in a little while to bring us back up. Then it gets too high again, okay, and we get thirsty, we drink water, brings it back down, and so forth. So we're going to try to keep it at this set point. So that's what these numbers right here are representing, really, is the amount of milliosmoles per liter. So we want to keep it at around 300. And when we start passing through the proximal tubule and the descending limb of the loop of Henle here, water is going to be passively pumped out here. And as a result, we're getting more and more concentrated fluid. And bear in mind all along when we're watching this, is we're just looking at one loop of Henle, one nephron here. But they're scattered everywhere throughout along with the veins. So they're right next to each other, right on top of each other, so on and so forth. So this is like a three-dimensional type of thing that we're looking at as well. And so they're everywhere. So this water that's being pumped out is being taken back up by the veins and arteries that aren't being shown here. Okay, so now we're getting here at the bottom really concentrated, about 1200 milliosmoles, about as concentrated as we can get. And then as we start moving back up the ascending limb of this loop of Henle, now we're going to start pumping the salt out, either passively or actively, depending on the color of the arrows here. And now it's going to get really watery here at the end of the ascending limb once we get towards the distal convoluted tubule, which is right through here. And now it's really watery. And then it's going to empty into the collecting duct. And you can see as it moves down the collecting duct, it's going to get progressively more and more concentrated again. And this is the part that's going to make its way to the ureter and then ultimately the urinary bladder. And along the way now, this collecting duct is the spot really where we're either going to reabsorb the water if we're really thirsty, or we're going to not do that and we're going to make a really dilute urine. So in this case, in this example here, we're reabsorbing a lot of water and we're making a really concentrated urine that's actually going to get out into the surroundings, obviously, like a really dark yellow urine would be really highly concentrated, would have very high milliosmol, like 1200 for instance, okay? So there's two main types of nephrons now. We've talked about, like, this is the nephron here, and there's two main types of them. You've got the cortical nephrons, the ones that are really towards the outside portion of the kidney, and those comprise about 80% of the actual neurons. They got a reduced loop of Henle, it's not as long, and they're really confined to the cortex of the kidney. And then the other one that we have about 20% of, these are the juxtamedullary nephrons. And these have well-defined, very long loops of Henle. And their main job is really to produce a very hyperosmotic or very concentrated type of a urine. Okay? And these are the key adaptations that allow organisms to be really terrestrial, to not be confined to an aquatic type of an environment. Okay? These are really our urine concentrating types of organs, as we said, and they get rid of waste really and not much water. Okay, so these things are going to produce a very concentrated type of a urine. And really each nephron now is aligned with a transport type of epithelium. And whether that tissue is actively or passively involved in transporting ions doesn't really matter, just the point that it's a transport epithelium or a transport type of epithelial tissue. This is what's important, okay? And this is what's going to regulate the reabsorption of solutes and water. So each day, your kidneys are going to filter, each one is going to filter between 1 and 2,000 really liters of blood, just depending on how big you are, how much you're drinking, things like that. And of that 1,100, 2,000 liters that gets pushed through there, about 180 liters of this filtrate is actually going to be formed. Okay, so vast majority of it isn't formed. And then of that, about 99% of all of the dissolved sugars, vitamins, and other types of organic nutrients, along with the water, are going to get reabsorbed. So you'll push between 1 and 2,000 liters of fluid through a day, and then just depending again on average about how much you drink is going to produce about 1.5 liters of water. So think about your water jug. If that's a liter, and many of them are either 500 milliliters or a liter, you're going to either produce 3 if they're 500 milliliters, or you're going to produce 1.5 if you've got a liter jug. So that's on average, but that's what becomes the urine. And if we look at the kidney now, we have an afferent arteriole, okay, and that's what's going to supply the actual glomerulus. And then you have an efferent arteriole, and this is what's going to really kind of move its way down and kind of really be integrated in and become a part of the actual, nephron, in terms of the nephron has the proximal convoluted tubule, loop of Henle, and the distal convoluted tubule. The efferent arteriole is going to branch out and become these paratubular capillaries, okay, and these are going to be involved in reabsorbing the things that are taken back up by the proximal and distal tubules. And then you're also going to have these vasa recta, okay, and these are the different types of arteries and veins that are really closely associated with this loop of Henle, and this is where you're going to have a lot of water exchange taking place and so forth. Okay, so here, if we look, this is the unit that we've been talking about. That's the nephron. Again, just kind of another picture of it. You can see the glomerulus, Bowman's capsule, proximal and distal tubules, the paratubular capillaries, and the vasa recta. And all of these things are going to be involved in getting as much good stuff out, water reabsorption, and then it's going to pass down to this collecting duct right here. And that's where you're either going to make a very concentrated or a dilute type of a urine. So the capillaries, we said, these descend down, so they're really running in opposite directions. So you can see this is the ascending limb, and if we look at this arrow here, the fluid is moving upwards in this portion, the ascending limb of the loop of Henle. And these blood vessels, the artery here is moving in the opposite direction, and that's by design. What's going to happen here is you're going to have like this countercurrent flow is going to allow you to maximize the amount of water that's being reabsorbed, as well as maximizing the amount of waste that you can get rid of. Okay, so we talked about the proximal cells really maintaining the pH within the lumen, the pH within the solution, and they're going to actively control the secretion of hydrogen based on the body's pH. So they're very closely associated with the lungs in terms of regulating the pH. We mentioned that earlier. And about 90% of the bicarbonate that you produce here this is also going to be reabsorbed as well, and that's also going to help, along with the hydrogen ions, of maintaining the pH. So you can think of the carbonic acid that we were talking about, H2CO3. Here are the two ions there. Okay, drugs like medicine, things like that you take, other types of poisons and so forth, these are going to pass from this paratubular capillary into the interstitial fluid, and then cross really into that proximal tubule, and then into the lumen of the nephron, so that you can get rid of these types of things. So there's kind of an exchange going on between the waste that you want to get rid of and the things you want to be reabsorbing. Okay. And then the useful nutrients, like we said, these things are going to pass from the lumen of the proximal tubule into the transport epithelial tissues. The interstitial fluid, that's the kind of the fluid that's bathing the nephron, the paratubular capillaries, all of this stuff. You remember, they're not in direct contact with one another. They're going to be bathed in a solution. It's important to keep that in mind as well. Okay, so one of the most important functions, as we said now, is to maintain the salt balance as well as the water balance within the system. Okay, so the sodium is going to diffuse into the transport epithelium, actively get pumped into the interstitial fluid. The chloride is going to follow, and water is going to follow by osmosis. So it's going to follow the concentration gradients being created by pumping the sodium chloride out of these tubules. And now the water and the salt can diffuse into this paratubular capillary and be taken back up. Okay, so the sodium chloride gets out, diffuses in, and then it's carried through. So now what's basically happening is you can see the blood that's flowing in this direction is reabsorbing the salt. Okay, and then as we get up here, you can see, if you remember on this side, on the descending limb, we're getting rid of the water. So now, because this contains, we're going to switch back over to the other side here, the ascending limb of the loop of Henle, you're going to either actively or passively get rid of the sodium chloride. So that's why as we move down in this paratubular capillary here, we're getting more and more salt, because that's what's being absorbed by the capillary as we go down, so it's becoming more concentrated. As we get down here at the bottom, we're very concentrated. Now, because the blood, the blue side here, is very concentrated in terms of salt, and the water is being pumped out of the descending limb, and it's being taken back up by the paratubular capillary here. As it's moving up, it's reabsorbing the water back into the circulation. So, that's essentially what's going on in terms of how this kidney is working here. Okay, so the descending limb is freely permeable to water. It's not permeable to sodium chloride. So as this interstitial fluid is becoming more and more concentrated as you go down, because you're pumping that sodium out, you can see that this water is going to flow out of the loop of Henle, and then it's going to be taken back up by the blood as the blood moves through the vasa recta. So again, we'll kind of come back to this picture here. You can see we're pumping. What's not being shown here is we're actively pumping out sodium chloride. We're passively pumping out sodium chloride. The blood vessel is moving in this direction. Sodium chloride is being taken up. It's becoming more concentrated. As the blood becomes more concentrated, again, this is the blood. As it's more concentrated, water is going to flow in to the blood vessel. And again, the blood vessel is not shown here, but as it moves up and then out, you can see it's going to be selectively reabsorbing this water that's leaving the descending limb of this loop of Henle. And it's because of the salt balance that you're maintaining. So this brown region right here, this is representing the interstitial fluid of the actual kidney. And if you look at the numbers over here, you can see near the top, it's right about at the set point. And as we go deeper down towards the medulla of the kidney, you can see we're getting progressively more and more concentrated, and that's having an impact on how this water is really moving. The reason water is moving out here is because it's more concentrated. It's 900 here, well, it's slightly more concentrated inside, so the water is going to move out. And then the blood is slightly more concentrated than that interstitial fluid because of the salt that it took up over here, and that's going to cause the water to move in. And all the while, this fluid, really, that's in here, even though it's changing concentrations as it goes up, it still contains these wastes. And when it gets to this collecting duct and begins to move down over here, this is where it's either going to be permeable to water or impermeable to water, and determine how concentrated the actual urine is when we get towards the end. Okay? So a lot of these words here are some of the things that we already talked about. This is the ascending limb moving up the loop here, and you can see that it's permeable to the sodium chloride, not the water, as we said. There's two regions to the ascending limb. Okay, you got two regions there. You've got a thin segment towards the bottom. Okay, and this is where you're going to diffuse sodium chloride out. And then you have the thick region, which is up a little bit more towards the top, right before you get to these distal convoluted tubules here. This thick region is where sodium chloride is going to be actively pumped out into the interstitial fluid, and it's going to have an impact on the things that we talked about. So you can see here, this is the picture again. You can see the red showing the active pumping of the sodium chloride, the blue, the passive pumping, and then the water, of course, all the way through here is being passively pumped out. And this is the way that this loop of Henle maintains the hypertonic kind of conditions of the medulla, like I was just saying, and being able to produce this urine as we start to leave this collecting duct. Okay, the distal convoluted tubule, again, just to kind of review, is going to regulate the pH just like we did in the proximal tubule. It's also regulating the amount of potassium ions that get out, sodium chloride concentrations in the body, so that's going to determine how much actually gets dumped into the urine, and it's going to selectively reabsorb some of the things and get rid of the other things. So the collecting duct now is what's going to be actively reabsorbing some sodium chloride, and the degree in which we are really permeable to the sodium chloride is under the control of the aldosterone, which we'll talk about in the next section. And the epithelial tissue really is going to be permeable to the water, but not the salt. So how this collecting duct behaves, determines kind of on the tissues we're talking about and any of the hormones that might be involved. Okay, so once you see the bottom here, as this collecting duct kind of traverses the kidney, it's encountering different concentrations of ions in that interstitial fluid, and that's what's going to allow us to produce perhaps a very concentrated type of a urine. Okay, the collecting duct itself is permeable to urea in the medulla down here, so you can see that the urea can get out when we get closer and closer to the medulla, okay, or the middle of the actual kidney. But in the cortex, which would be out here, okay, it's not permeable to any of the urea. But that urea is going to kind of assist in making the medulla more concentrated, so we can concentrate that urine even more. Okay. So next time we're going to talk a little bit about the mammalian kidney more in terms of how it's under hormonal control. We talked a lot here about how it's really under the, I guess you'd say, as the sodium and the chloride move through the various tissues, how this thing is involved in creating that filtrate that has all of the bad stuff in it and the good stuff taken out, or the waste in it and the good stuff taken out, the nutrients taken out, and in addition how a lot of the water is reabsorbed. Okay, so next time now we're going to talk about the hormonal control of the kidney. So if you have any questions, make sure you write them down. If not, we'll talk to you soon.